Yeah.
Okay, I'll get started because the first little bit of this isn't too bad. So I think one of the things there was one. Was it last year? I don't think the paper I gave last year wasn't too. I didn't give you shocks last year in a different exam. That's true. People were a bit put out by this exam. I think kind of what I could have done is I could have put more of the easy questions at the very start. So the first question, which was actually really easy, threw some people. So that issue isn't there, but actually this question isn't difficult. So the first thing is, that's basically just resistors in series with resistances X and Y. And the first thing is show that the total resistance is given by that. So basically solve this equation for R.
Can you order the sheets there, JP?
Yeah. Thanks. So if you're trying to solve this for R, what's the biggest problem?
Two unknown fraction.
Two unknowns. It doesn't really affect you. There is a clever, yeah. It's under a fraction is the issue. So it's down here. That's bad. Now there is actually a kind of a bit of a nuclear bomb here you can throw. If you do 1 over R on both sides, or 1 over on both sides, you can clear that up. But usually we're not so good at that. So say we get rid of the R on the bottom. How do you get rid of that R? Multiply by R. And you know what? While we're at it, we may as well just get rid of the X and the Y. You know, fractions, we don't like them. So we're going to multiply by R, we're going to multiply by X, and we're also going to multiply by Y. And remember, 1 over something is basically dividing. So multiplying this by R by X by Y, so you basically got R by X by Y divided by R. What will that be? X by Y. Here, multiplying by this, you're going to have R by X by Y, basically divided by X. What do you have?
RY.
RY. And then plus this one, you're basically going to have R by X by Y divided by Y.
RX.
RX. Now you're trying to find R on its own. Now one thing, just for no particular reason, it's, well, just because we read left to right, we might put what we want on the left. So if this is equal to that, that's equal to that. So we actually have RY plus RX equal to X by Y. Actually, this is a little bit like some parts of Laplace, where you didn't have 1 y of s plus 2 y of s, you had sy of s plus 3 y of s, and you didn't kind of count them, you took it out as a common factor instead. And that's the same thing you do here, take out the R, and you're left with y plus x equal to x by y. I'm going to get R on its own. How to get rid of that y plus x?
Divide by
Y by y plus x. And of course y plus x is the same as x plus y. So divide by y plus x, so that's xy divided by x plus y. So that's the first bit done. Now you're going to have a question tiny bit similar to this, and what you're going to have to do is basically, you mightn't have to solve for anything as far as I know, but it's going to ask you maybe to partially differentiate this thing. If I was to kind of take it back and do this question again, I'd throw in R1 and R2 and ask you to differentiate partially with respect to R1 and R2 rather than using X and Y. And then what I could ask then about the derivative would be, well, for example, this is the resistance increasing or decreasing as X increases, and you know that by looking at the sign of the partial derivative. So the second bit is find partial R, partial X. So differentiate this thing with respect to X, keeping Y constant. Now, what's the big story for differentiating this thing? Okay, keeping the Y constant is the partial derivative, but in terms of rules and that, what's the big story here?
Quotient.
Quotient rule, exactly. So you take out your big tables and you get, open up calculus and get the formula for differentiating quotient. And I'll probably just label that here. So we're going to have partial R, partial X. So you differentiate away, treating Y as a constant. So the formula is the bottom, X plus Y. I'll write in the V afterwards. Times. Now, if I write times, I'm actually heading for a little bit of trouble here. If I want to do the X, I should have a bracket here. Because it's a sum, otherwise, strictly speaking, what you write down is wrong. So that's the bottom by the derivative of the top. Now you're differentiating this with respect to x, keeping y constant. So basically you have a constant times x, and what we're doing the whole time is fix your constant y, and then differentiate your function of x. What's the derivative of x with respect to x?
1.
1. So that's the bottom by the derivative of the top, minus the top, which is x by y, no need for the bracket because it's all multiplied together, times the derivative of the bottom, which will need a bracket. What is the derivative now? This time it's a sum, so you can do term by term. What's the derivative of x with respect to x?
1.
1. Plus, what is the derivative of y with respect to x?
0.
0. Good. All divided by the bottom squared. So just in terms of the formula, if you're looking at this, the bottom by the derivative of the top minus the top by the derivative of the bottom, all over the bottom squared. Now this, how many marks? 3 marks. There's possibly 2.5 marks there, or maybe 2. Really, that should be tidied up. You've got x by y is xy. So you should multiply out the top. You have xy plus y squared, and then you have minus xy by 1. Now, so you have xy minus xy is 0. You'll just be left with y by y, which is y squared, over x plus y squared. Now, a question that you could be asked at this point to be something like, does total resistance increase with x?
No. Decrease.
Increases.
Sorry, did you say that y squared is actually equal to the top line, is it?
Yeah.
Is it?
X by y is xy.
Oh.
Xy by 1 is xy. So xy minus xy is 0. And y by y is y squared.
Oh.
No, that's positive, which means that the total resistance increases with x. Okay, so that's the first one.
So did we work the formula for the response there?
In the tables, quotient rule. Big tables. So remember the tables I used to throw out before, the derivatives and stuff?
Page 320.
But now you're not going to have that on in the big exam, you're going to have this here. So here it is, look, the bottom. So the top is u, the bottom is v. The bottom by the derivative of the top minus the top by the derivative of the bottom over the bottom.
Just before we move on there,
Yeah.
so you have x, r, x, y. I don't understand that as well. Like you went from the top line down to the second line. And
Yeah,
like I
so
don't understand
I want to get rid of the r because the thing I'm looking for isn't a fraction. I hate that, but I also just hate fractions anyway. So I want to multiply by x and multiply by y as well. Because I don't want fractions. That's crap.
Oh yeah.
So if I that's why I'm multiplying by r. And if you multiply, say if you multiply by 5, and then you multiply by 6, what have you actually multiplied by?
11.
No,
Oh, no.
30.
Oh, 5 or 6.
Say take 2 quid, multiply by 5, you get a tenner, multiply that by 6, you get whatever, 60 quid. So if you're multiplying a couple of this and then this, well, you're multiplying by them all multiplied together. Now do you understand how multiplying that by rxy gives you that?
Like I know if we multiply by r, you're going to get rx plus ry.
If you multiply by r, what's r by this?
1.
1, yeah. And r over x, and r, yeah, that's right.
And then
Then
multiply by
multiply by
xy
x.
is going to be xy equals r
Or
plus
y, because r was there,
Yeah.
and then y, and then rx. So if you want, you can slow it down a bit if you want for yourself and do, a few steps, but ultimately it's going to follow that.
But there's another x there, like, or there's a multiply sign. See the blue?
Oh, that's a multiply, sorry. Yeah. Okay. So the next thing then we're looking at, question B. Any questions on that? So basically, the other thing that can happen here is maybe I don't give you this. Maybe I give you something more like this. Now, it's not going to be resistant, right? But so I give you something, and I ask you maybe to differentiate with respect to x, differentiate with respect to y, and then I might add, the thing I might be interested in here is, well, what happens to this when x gets bigger? What happens to this when y gets bigger? If the derivative is positive, your function gets bigger, and if the derivative is negative, it gets smaller. Okay.
If you 1 over r is equal to 1 over r1 plus 1 over r2, would you still?
Yeah, if I was to take it back, you see, I think probably I probably wrote the 1 over r1 and 1 over r2 first. But then when I got down to here, maybe I was worried that people only really differentiate with respect to x and y, but actually that isn't true, because in your error analysis you have to differentiate to whatever. So the x and the y are the r1 and the r2. Is there a different question there?
Yeah, sorry, say that again. If the derivative gets smaller, so in that case it's going to get smaller as y gets bigger.
No, this is positive. Like this is the rate of change of total resistance with respect to x. It's positive because it's squared over squared. So as one of the resistances, as this gets bigger, the total resistance gets bigger as well.
Alright, okay.
Second one. Now now here this one possibly, so people hadn't seen something like the first one, and the second one they'd seen. So this is your Newton-Raphson, but maybe the question hadn't been something like this. Your one will be it'll be kind of set up, and you have to take your time and go through it and read the question properly. So what I got, this normalized sinc function is a function used in signal processing, defined like that. Show that the equation sinc of x equal to a half can be written like that. So the first thing, the sinc of x equal to a half. So sinc of x is sine pi by x over pi by x equal to a half. Now basically the job of this question is to solve sinc of x equal to a half, but if you remember, Newton-Raphson is set up in such a way that you find roots, you find things equal to 0. So basically the job really was write this in the form something equal to 0. Now the thing you have to solve it for is there, in fairness, but you could, I won't ask you for this, but in theory I could say, well, off you go. Set it up to be solved equal to 0. Now if you're looking at this for solved equal to 0, you could kind of just take the minus a half away from both sides, but that made the differentiation later more difficult, so that's probably why I set it up that way. So if you're looking at the thing it had no fractions in the end, so I want to get rid of the pi x and I want to get rid of the 2. How do I get rid of the pi x? Multiply by pi x. And how do I get rid of the 2?
Multiply by 2.
Yeah, so you multiply by 2 pi x. Now this is what would be called, people would use the phrase cross multiply, but I hate that because it lends people doing all that stupid crap. So if I multiply this 2 pi x by this, well, the pi x divided by pi x is gone. I'm left with 2 by sine pi x. And if I do, this is 2 pi x by half, I get pi x. Let's have a little look at my thing. And it's just 2 sine pi x minus pi x equals 0. So I take away the pi x from both sides and I'm done. So that's that. First bit done.
Simple as that.
Yeah. Show that this has a root between 0.5 and 1. Now, strictly speaking, if you're to this different course, explain what's continuous. Everything we give you will be continuous. So, how do we show that this f of x has a root between half and 1?
Make it equal to 0.
Well, we want to show that it's equal to 0 between a half and 1.
Substitute value?
Substitute in a half and substitute in 1. We'll just see what happens if we do that. F of 0.5. Now the f of x is given in the question, I think. Yeah. So this would be 2 sine pi by 0.5 minus pi by 0.5. Now, there's one thing that you're looking out for anytime you're doing calculus with sine and cos. What are you looking out for?
Radians.
Have to be in radians. So if I calculate this, I'm going to get 2 minus a half pi. I'm getting, now it actually doesn't matter what I get. At 0.429, what's the only really important bit?
Over 0.
Over 0. And then look at the same thing at 1. 2 sine pi by 1 minus pi by 1. This is actually equal to 0. So this is equal to minus pi, and the important thing is that it's negative. So the function went from positive to negative. So what certainly happened?
Has a root.
Has a root across the x-axis. So you're just going to say root in, well, transfer, you're right, that you're done. But you can do a little bit more as like that. Basically the graph had to cut the x-axis. The graph, well, it cuts the x-axis when the y coordinate is 0. And of course you plot the f of x, so if the y coordinate is 0, the f of x is 0, this is the f of x, so this guy is equal to 0.
I said first was 0.4, was it?
Doesn't matter. The important thing is that it's bigger than 0.
So that one just basically put in a value for x.
Put in no, but the either end of the interval. So show that it has a root in that interval. That means show that it has a root between 0.5 and 1. So bang in 0.5, bang in 1. Yeah. Hence use the Newton-Raphson method twice with this seed to approximate this root. So probably what you're going to do at this stage is you're going to write down, you're going to take out the tables, page 25 or whatever it is, and you'll see this formula. The next approximation to the root is the previous approximation minus the value of the function at the previous approximation divided by the derivative at the approximation. Now, my interest with this question was to get something that was eventually relevant to sinc function. Possibly with the derivative there's a little chain rule, so people went a little bit wrong, but I mean small things like that aren't really affecting the big marks. Do you understand? So I mean if you're getting little chain rules wrong or something, it's not the end of the world. So definitely what we're going to need here to look at this is we're going to need the derivative. This is f of x, we need the derivative of this. So we may as well do that down here. Now it's two terms added together. One of them is negative, that's okay. So you can do term by term fixing constants. So fix the 2. Now differentiating sine of pi x is probably what most...
Just on the first one there, see the second line where you have the equals to pi x.
Yeah.
If you stop there, would you still get most of the marks? Or?
Don't stop there.
No,
I
but
mean
just
that's...
look-
I know, but you're going nowhere. You're actually like something like that. I'm like there's a balance between playing the game and basically just trying to get the earliest part out of it. Like here, if you're stopping there, you don't know what you're doing. Overall, I mean you're trying to get solving things equal to 0. Yeah, but look, that's on the paper.
Yeah.
So
For the first one there, the f.5, my calculator just got 0. You said you got more than 0, did you? That's what I was asking.
sorry.
0 as well, did you?
No, in radians.
Yeah. I just obviously typed it in wrong and do it again, doesn't matter.
No, you see, this is 90 degrees.
Yeah.
So that's sine of 90 is 1, so that's 2. Half pi is 1.57, so it's
Yeah, I just typed it
definitely...
in wrong.
Yeah, okay.
See your xn plus 1. Where, I know at
Page
least
25 tables.
35.
20, is it? I don't know.
Is it? I'm on 25.
Starting at page 25.
Starting.
Yeah.
Good man yourself.
I'm just saying that that's where
Oh,
these
I see
calculus
now,
formulas are. Yeah. I'm going to write page 25 because it's very, that's where all, you don't want to be thinking 20 different pages for, just
Yeah,
something they
exactly.
start around there.
It's in
No.
the tables anyway.
It isn't.
What page? What's the conclusion? Those my feet. This is math, Sean.
Now, So if someone turns around and says the derivative of, I'm going to do some color coding on this for a second. If someone kind of goes along and says the derivative of sine of pi x is cos of pi x, you know, and drives on, it's wrong, but look, they're going to pick up a lot of the marks. That's more the thing. So like, if you're not strong with the chain rule, don't be freaking out about the chain. You know, that's kind of what I'm saying. Now, of course, that's not quite right. If it was sine of x, it would be cos of x, but it's sine of a function of x, so you have to use the chain rule. The chain rule says, and the chain rule comes into other questions, so it's not like you totally ignore it. So you have an outside and an inside. So the chain rule says differentiate the outside. What's the derivative of sine of x? Cos of x. Chain rule says evaluate it at the inside, that's evaluated at pi x, and then times the derivative of what's inside. So pi is actually, it's just a constant. So fix the constant pi, and then what's the derivative of x? 1. So derivative of pi x is pi. So that's actually the derivative of that. Minus the derivative, and we also have minus, fix the constant pi as well. What's the derivative of x with respect to x? Still 1. So we just needed that guy there. Now it's telling us where to start, and I'll